And welcome back, everybody, to this third video of our pre-cal. I hope that you are slowly digesting the material of the previous ones. Today we are continuing our exploration of factoring. That'll be the second one on factoring. Remember last time we did simple factoring, and today we will explore factoring of squares and cubes. And I should actually mention before we start that many high schools don't actually cover the factoring of sum of cubes and actually difference of cubes. That's the one I was looking for. So you might actually learn something completely new today. For some it will be review, and for many it will actually be new stuff. So without any further ado, let us explore our first case called difference of squares. This is not a new one. Everybody probably has been exposed to difference of squares in high schools. So what is a difference of square and what can we do with it? Well, as the word suggests, this is actually something of the form something squared, 8, let's say, something else squared, and the word difference suggests a subtraction between the two. Anything that looks like something squared minus something squared can actually be factored as, oh, you know this, right? Of course you do. It's a plus b times a minus b. The proof of this is super simple. All you got to do if you want to prove this formula is what? Well, take the right-hand side and expand it the way we did it in the previous videos. So a with a with b, and so on and so forth. And you will see that things cancel out until you get back to a squared minus b squared. Petit exemple, example 1 on this. Let's start slow. So what shall we say? Factor completely. That's usually the way we word these finds. Factor completely something like x, 2x to the power of 2 minus, what shall we put here, 8y to the power of 4. All right, so 2x squared minus 8y4. Question, can I consider this, the first guy, a perfect square? Is this writable as something in a bracket with a square outside? Think about it. What would you say? Yes or no? No, huh? Because of, well, yes, maybe if you put a root here, root of 2 times x, but we're not going to do that. We're not going to go into roots. We're going to stay with whole numbers because most of the calculus that we have to deal with later will actually involve this. Not all, but most. So my point is this. This is not right away a perfect square, but it could very well be if we start with a simple factoring the way we know how. Do you see anything common between 2x squared and 8y4? Do you see a common factor, in other words, between this and that? And if you answered 2, then you got a winner. You can totally take out a 2 from 2x squared minus 8y4. So let's do just that. X squared minus 4y4. And now the question arises, is this a perfect square? And is this a perfect square? And the answer is yes, because this is the square of what? It's the square of x. And the other dude is what? What is this guy? Is it a perfect square? Yes, it's the square of 2y squared. Yes. Yes. So basically, let me carry my 2 over here. Voila. And then I got my perfect square. So this is my A, and this is my B. So in this case, A is x, and B is 2y squared. Simple as that. Simple as that. So now I apply my formula. I shall now write this as a plus b times a minus b. So I carry my 2, and I shall have a plus b times a minus b. What's a? A is x. Plus b, what is b? 2y squared. And then the bracket is exactly the same thing, the next bracket, except it has a minus. And that's it. That's the factoring of the original 2x squared minus 8y4. We can box this should we want to because it is our respuesta final, the final answer. Okay, so difference of squares, that's pretty much how it goes. Let's do an example 2 on this. Let's make example 2 a little more challenging, perhaps. This whiteboard is not conducive to being erased. Gotta fight with it. It doesn't want to be erased. Example 2. Let's bring this up to 3 stars. So this time we want to factor completely. I have something here that I want to give you. 4x3y minus 16xy3. Well, it's 3 stars because there's a few more variables, but it doesn't mean it's really that much more complicated. So, how would you like to start this? Do you think you can write this guy, 4x3y, as something that is a perfect square, that is something with a power of 2 outside? Well, the 4 is okay, because that would be 2 squared. But the x3 doesn't work and the y doesn't work, right? So I can't go straight away into this. So perhaps I can factor out something. Perhaps there can be a simple factoring that I can do on this. Between 4 and 16, for sure, I can take out a 4. This has an x cube and this has an x1. So I can take out, remember, the common factor with the lowest power, so x to the 1. This has a y to the 1 and a y to the 3, so let's take out a y. Okay, now we're fairly good at this. If you remember how to do that, we go aside and we go 4x3y, the first term, divided by the common factor, the CF. Remember we did that before? I'm going to go a little more quickly over this now. So this is the first term divided by the common factor. If you do that, the 4's go, the y's go, and x3 divided by x1 is x2. Can you actually find what would be left if I take out 4xy from 16xy squared? Can you do this? Can you do this here? What would we get? Well, the second term, 16xy3 divided by 4xy to the 1, that should give us 4y squared. And now, this is a perfect square, isn't it? It's the square of what? It's the square of x, may we? And this guy is the perfect square of what? Well, it's 2y, of course. So, keeping this here just the way that it was and putting brackets here, we now have a squared minus b squared. So the a in this case and the b are simply what? That's my a and that's my b. X and 2y. So that's it. Once you've done this, you apply the formula and you're homeward bound. So this is equal to 4xy. So I forgot my minus here. So this is my a. So a plus b, a minus b. That's my formula, right? A plus b, a minus b. So a plus b and a minus b. Et voila. That is the final answer. I don't really know if that's worth 3 stars. Whatever, I'll let you be the judge of that. Maybe 2.5. So that's difference of squares. Okay, good. So that's the one that pretty much everybody sees in high school. Now let's take a look at the ones that people don't see so much in high school, and it involves the power of 3. That's why we call them cubics. Cubics. Cubics, cubics. Look at this, man. This is horrible. Maybe that's my eraser that's really not so good. This works a little better. Okay. All right. C'est bon. So difference of cubes. Second case. Second case. Difference of cubes. As the word suggests, this is when I have a cube minus a cube. So the formula here is a cube minus another cube. So this situation will apply every time we have something that can be written as bracket power of 3 minus bracket power of 3. Formula for this, a minus b multiplied a squared plus ab plus b squared. How would you prove this formula if you were asked to do so on a test? Simple, expand the right hand side. So a times a2, sorry, to give you a3, a times ab will give you a2b, and so on and so forth. Collect, like terms, cancel, and you will get back straight on to a cube minus b cube. All right, exemple 1 for this. So let's start this at 2.5 star. So factor completely. Factor completely the following expressions. Let us say we have x to the power of 6 minus 8. Okay. Is that a difference of squares? Maybe that's like we saw the case before. Do you think that x6 could be written as a perfect square? Yeah. x3 to the 2 is x6. That's a perfect square. But the 8 is not. 8 is not a perfect square. It's actually the square of 2 point something. It's not a whole number. So we're not going to be happy with that. But we may actually try, in light of this new difference of cube situation, we might actually try to write this as something to the power of 3 minus something to the power of 3. What would you put in there such that when you raise it to the power of 3, you are going to get x6? And if you answered x2, you're very right. Very easy to check. Rules of exponents, the most fundamental thing in the course. Rules of exponent. When they are next to each other like this, we multiply them, so 2 times 3 is 6. So that expression to the 3 is correct. It gives me x6. What about 8? Is 8 the cube of something? Bien sûr. It is the cube of 2. 2 to the 3 is 8. As soon as you can write something to a 3 minus something else to the power of 3, you have a difference of cubes. In other words, I got an A and I got a B. What's my A and what's my B? Well, A is x2, B is 2. Once you've identified this, if you know the formula, you plug it in. Et c'est tout. Alors, let's do this. Let's do this. So x6 minus 8, written this way, shall be written as a minus b, a minus b. So a x2 minus b 2. So that's the a minus b in the expression here. And now this one, a squared plus ab plus b squared. So a squared x2 squared plus ab. So again, ab x squared times 2 plus b squared. And that is pretty much the correct expression. Can be simplified a little bit, claro, no? So x squared minus 2 and x squared squared can be written as x4. X squared times 2 looks weird, right? The x squared in front of the 2, so we're going to make it look less weird. We're going to write 2x squared, and 2 squared is 4. And that's our final answer. If you're thinking, can I refactor this expression here? The answer is no, you can never refactor this. We're going to cover factoring trinomials in the next video, not this one. And we're going to see for some reason that this cannot never be refactored when we have a difference of cubes. So that's our final answer. And that's how we actually factor out the difference of cubes. Let us see if we can do another one that is perhaps a little more challenging. So maybe we bring this up to 3 stars. 3 stars. Exemple 2. Factor completely. Yeah, what have I got here? A to the 6 minus 27b to the 12. All right. A to the 6 minus 27b12. So the challenge here is always the same thing. Can I write these guys as either a sum of a difference of squares or a difference of cube? There will never be a difference of squares because 27 is not the square of anything, but it's the cube of something. What is 27 the cube of? What number raised to the power of 3 is going to give me 27? You got it. It's 3. So the challenge is to come up with what goes into these brackets once they're affected with the power of 3. So a6 must be written as something to the power of 3. Shall we say a squared? Once again, why? Because exponents are multiplied to each other, so 2 times 3 is 6. As for the 27, we already discussed that 3 to the power of 3 is 27. As for the B12, like the vitamin B12, what do I write here that actually, once I raise it to the power of 3, gives me 12? Well, what times 3 is 12? It's 4. So, not after, but before. Get it? Before. So, 4 and 3 is 12. I think we got ourselves an A and a B. All right, so in my formula, A is going to be this A squared. So A is going to be this A squared. And B is going to be, again, in my formula, this other guy that we called 3B4. Okay. So once again, that was the challenge, to identify the A and the B. It's not much of a challenge to actually replace them into the formula. So A minus B, A minus B, yep, times A squared, so A squared squared, plus AB plus A squared 3B to the 4 plus 3B to the 4 square. And that actually covers the trinomial that is here. Of course, we can simplify this a little bit by, again, using what? The most important rule in pre-cal, the rules of exponents. So A squared squared, that would be A4. A squared times 3B4, we're going to put the constant in front and we're going to put our variables in alphabetical order, so A squared B4. And finally, 3B4 to the power of 2, that would actually be 9B8. And that's the final answer. If you're wondering if you can actually refactor this as a difference of squares, the answer is No can do, because 3 is not a perfect square. A squared is a perfect square. B4 is a perfect square. 3 is just the square of root of 3. Not so good. Okie dokie. All right, all right. Ah. So, difference of cubes. Difference of cubes. Done. There is another formula in this chapter that you may not have seen in high school, and it's the last and third object of this video, sum of cubes. Oh yeah, sum of cubes. This one happens when you have a cube and another cube, so two cubes that are actually added together. So there is a formula for that. If you've seen it in high school, you may remember that this goes as a plus b times a squared minus ab plus b squared. Once again, how do I prove this? I expand the right-hand side, collect my like terms, do the proper cancellation, and I will fall back on my feet with a3 plus b3, guaranteed. Guaranteed, guaranteed. Exemple 1. Let's do this as 2.5 stars. So factor completely. Factor completely. What shall we have here? What about something like x9 plus 1? All right, let's keep it simple. x9 plus 1. I claim that this is a sum of cubes because I can write this as something cube plus something cube. Let's see what we can put into these brackets so that we have a cube plus a cube. If you're saying that 1 cube is equal to 1, you're absolutely correct. What about this? What goes to the power of 3 here? Well, it certainly should be x3 because 3 times 3 is 9. So what I have here as my A and as my B are x3 and 1. Very good. Very good, very good. So, doing my A plus B here, I get x3 plus 1. And then doing A squared, so x3 squared, minus this time, x3 times 1 plus 1 squared. So that would be x3 plus 1 times x6 minus x3 plus 1. Would that be my final answer? Well, remember now, we're into like more complex problems. This is factored completely. This guy has not been factored completely because this is again a cube plus a cube also. This is now x here plus 1. That is another, inside the sum of cubes, this is another sum of cubes. So we have to refactor this, and this time here, our A is x and our B is 1 in this refactoring of another sum of cubes. So what do I get? I get x plus 1 times x squared minus x times 1 plus 1. Let's not forget that we also have this other guy here that is x6 minus x3 plus 1. And now this is complete. Good problem. Good problem. Two sum of cubes within the same problem. So that maybe requires a little more than just 2.5, maybe 2 3/4. So let's have another one. Factor completely. What shall we have here? I have something here that I prepared. Factor completely. So shall we say 3 stars? For example, 2. Factor completely. 8x 9 z 6, so 2 variables, plus 1 25 y cubed. Once again, this looks complicated, but we can simplify it so much if we make the effort to try to write this as a cube plus another cube. It's not always possible, but when it is, then we actually do have a nice factoring case. So let's see. Can I write this as a perfect cube? Well, is 8 a perfect cube? Well, sure. 8 is actually 2 to the power of 3. X to the 9, is that a perfect cube? Sure thing. It's the cube of x3. Once again, x3 to the 3 is x9. And z to the 2 is z6, because 2 times 3 is 6. So we got here a perfect cube. What about the 125y cube? Oh yeah, 125 is actually 5 to the power of 3. And y to the 3, well, I can just write y to the 1 like this. So I have here that 2x3z2 and 5y are respectively my a and my b. And once this is established, I guess the worst of the job is done. Plug it in here. So egal, a plus b, baby. So 2x3z2 plus 5y, that's a plus b, times a squared, so this ugly thing squared, oh, minus, sorry, I was going to put a plus here, but I would be wrong because it's not a plus, it's a minus. So minus a times b, so minus 2x3z2 times 5y, so that's my minus ab term, and then plus b squared, so plus 5y all squared. So to actually get a final answer that we can box, we should probably make the effort to simplify the second bracket. 2x3z2 to the 2, that is certainly 4x6z4. Agreed? 2x3z2 times 5y would actually be minus 10x3yz squared, plus the final one is easy, it's 25y squared, and that is the final answer to this 3-star problem, sum of cubes. C'est bon? C'est bon, c'est bon, c'est bon, c'est bon. So let's do one last problem. Let's do one last problem for today. Something that would perhaps encompass a bit of everything that we have seen in this segment of the course. So, summary problem. So one last one for the road, like they say. So factor completely, what do I have here? 3x to the 8 minus 768. All right, let's give this guy 3.5 stars. Let's give this last example 3.5 stars. All right, 3x8, is that a perfect square? No, 3 is not the square of anything. Is that a perfect cube? No, 3 is not the cube of anything. What does that suggest? Now we should actually look for a common factor between this guy and this guy. Is there a common factor between 3 and 768? That's another way to say, does 3 go into 768? And the answer is yes, it does. So take out a 3 from 3x8, you're going to be left with x to the 8. And take out a 3 from this, you're going to get 256. All right. So what do we got here? x8 minus 256. Do you think x8 is a perfect cube? Would that be the cube of something? Can I write this guy as a perfect cube. So x to the what, if I raise it to the 3, would give me 8. Is that a whole number? No, because the answer to the question mark is 8 over 3. So that is not a whole number, so that is not a difference of cube. Maybe it's a difference of squares. Would that be a perfect square? For sure, it's the square of x4. Would that be a perfect square? Yes, it is the square of 16. All right, so here, my A is x4, and my B is 16. And what I have is a squared minus b squared. That's now back to the first case today, difference of squares. So difference of squares, what am I going to get? I'm going to get 3x4 plus 16 and x4 minus 16. Aha! Factor completely takes its full meaning here because I got a feeling that x squared minus 16 is yet again a difference of squares. So that would be the square of what? x4 would be the square of x squared, while 16 would be the square of 4. So now this stays, but this is the one you know well. So x4 minus 16, difference of squares, x2 plus 4 and x2 minus 4. Oh my God, this is again a difference of squares. So like a third difference of squares within the same problem. So 3x4 plus 16 times x squared plus 4. And finally, the last difference of squares, this is x minus 2 times x plus 2. And that makes the final answer to this problem. So of course, when we meet in class, we're going to cover more of these problems. We're going to do more examples, but that's the gist of it. So I hope that this brings back some memories, good or bad, and maybe you've learned about the cubes if you haven't seen that in high school. That's important for this course because it's important for Cal 1. That's it for today. I wish you well, and I'll see you soon.